All right, and then finally, I talked about this in the previous slide about a tree diagram. Tree diagrams are very good ways to find the sample space of conditional probabilities. All right, so this problem is looking at whether or not you hit the snooze button and whether or not you got to school on time. Okay, so a tree diagram, we always start with an individual, whatever it is we're talking about. So we start out here with nothing. What are the choices? It's not always 2, sometimes it's 3, 4, or 5. But what can happen when your alarm goes off? 2 things. Either you hit the snooze button or you don't hit the snooze button. We know from previous experience that the probability that Shannon will hit the snooze button is 60%. So the probability of hitting snooze is 0.6. Therefore, the complement of hitting the snooze button would be not hitting the snooze button. So this would be, you want to think of this as S and this as the complement of S. Okay. Now, given that you hit the snooze button, 70% of the time that you hit the snooze button, you will make it to school on time. 30% of the time, 70% of the time you hit the snooze button, you make it on time. 30% of the time you hit the snooze button, you don't make it on time. Okay. What if you don't hit the snooze button? Well, then you make it to school 90% of the time on time. Therefore, 10% of the time you're late, even when you don't hit the snooze button. These probabilities right here, this second group of probabilities, are conditional probabilities. This 70% is the probability you make it to school on time given you hit snooze. So the probability that you are on time given that you hit snooze equals 0.7. These are conditional probabilities. Okay. This one here, let's look at this 0.1. That's the probability that you were not on time given that you did not snooze, which is 0.1. Okay. So this is a great way to represent conditional probabilities. Let's erase this chicken scratch on here and look at another example. Okay. What is the probability that you show up to school on time? So what is the probability that you're on time? Well, how can you get to school on time? That's the probability that you hit snooze and you were on time, or the probability that you did not hit snooze and you were on time. We need to talk about stuff in terms of and, or, given. Then it's going to make things a lot easier for us. So the probability I hit snooze and was on time. I hit snooze and was on time. So I'm trying to find the probability. This is out here would be the probability of snooze and on time, which equals the probability of snooze times the probability of on time given snooze. Well, the probability I hit snooze is 0.6 times the probability I'm on time given I hit snooze is 0.7. So the probability that I hit snooze and I'm on time is 0.42. Or I could also be on time, or I could also be on time. The probability I don't hit snooze and I'm on time. So the probability I do not snooze and I'm on time. The probability of not, this is the probability of not snoozing times the probability of on time given I don't snooze. So the probability of not snoozing is 0.4 times the probability of being on time given that I did not snooze is 0.9. So the probability of not snoozing and being on time is 0.36. So the probability on a randomly given day that you are on time to school is 0.78 or 78%. Not very good. You better get to school on time more than 4 out of every 5 days. Okay, so that's how we would use this tree diagram to make our life way, way easier. Okay. There's lots of different types of questions that we could ask like this. The tree diagram, again, is for sequential events, okay? Probability to hit snooze, given that I'm on time. So anytime we have sequential or conditional, we're going to really like to use this tree diagram to try to model that. One more example here before we finish up this chapter. I want to know what is the probability. No, I lied. We're done.